Previously in this module, we presented an original approach in composite material management entitled Temperature-Assisted Reshaping of Composite Parts. This approach is adopted to reform or reshape an end-of-life curved composite piece to turn it into a flat piece that can be later on used as a panel for furniture or vehicles of public transport. In this video, we shall get into detail on the study of geometrical stability of the reshaped composite pieces. This requires a series of steps to ensure that the final product can retain its new form for the longest time possible. Here's a quick recall of the reshaping method. A curved composite part made of glass fibers and polyester matrix is fed between two counter-rotating hot rollers or counterparts of hot press at predefined temperature and pressure. The polyester resin was found out to soften at 90 degrees centigrade, which makes the composite softer and easier to reshape. After exiting the machine, the composite part shall retain a flat geometry so that it can be used in other applications. So, how can we make sure that this change in shape is stable? The answer comes as a series of steps. The main idea is to set a testing protocol that involves the necessary parameters and conditions affecting the shape stability. The composite that will undergo this protocol was introduced in the first video, but here's a quick recap of its composition. This being said, the composite was fabricated using a semi-cylindrical mold with a radius equal to 600 mm, giving the piece its initial curved shape. The protocol involves two main parts: reshaping and recovery. Reshaping is realized by inducing the desired geometry to the composite by placing it in a closed guide made from two pieces of plain wood and joined together with bolts, as shown here. Both the guide and the composite are heated at 90 degrees centigrade before assembly. After 30 minutes, the initially curved composite is placed between the two guide pieces and tightened until the composite becomes completely flat. The whole is then heated for another 24 hours at 90 degrees centigrade, then slowly cooled to room temperature without disassembling. Recovery is the next step. After dismantling the parts, the geometry of the composite specimen is traced. Then, each one is heated at a certain temperature for a predefined period of time, and the geometry is retraced and compared to the previous one. The measurement corresponding to this geometry change is referred to as recovery. The collected data show the effect of temperature on composite recovery. As the temperature increases, recovery becomes more significant. It's obvious, however, that at 25 degrees centigrade, the composite is not capable of retaining a flat shape. This is attributed to the elastic effect of glass fibers embedded in the composite. A new guide is hence put in place. Instead of flattening the composite, it forces it to bend in the opposite direction. The initial shape is positive curvature, a flat shape is zero curvature, and the counterbent shape is negative curvature. So, bending the composite in the opposite direction along with post-heating suggests that positive recovery with negative curvature would result in a stable flat shape, or zero curvature. The same testing protocol is then applied with two counterbending radii of 600 mm and 2000 mm. From the results, it's clear that the hypothesis of counterbending can be validated. At ambient temperature, the composite can retain negative curvature for a reasonable amount of time, and it reaches stable or zero curvature after more than 1,500 hours. For the radius effect, bending at 600 mm seems to be more effective, as bending at 2000 mm does not induce enough deformation. Finally, heating the specimen produces similar effects to flattening, but with a more stable recovery over time.